Okay, so our next talk is on automatic resource analysis with Coq proof objects, and Quentin is going to give the talk. Please go ahead.
Thank you. So this is joint work with Jan Hoffman from CMU, Tom Rebs from Wisconsin, and Jean Chao, my advisor at Yale. So the problem we're trying to solve is like in the previous talk, we want to find a resource bound on the consumption of programs. The motivation for this are, for instance, economic. So if you have a less resource-hungry program, you can have a cheaper computer, and this is important, for instance, for mass-produced embedded systems. For safety, too, in a hard real-time system, you want to make sure the latency is within safe bounds. And for security, for instance, constant time to check that implementation of cryptographic primitives are in constant time to avoid side channel attacks. So the goals of this specific work is we want to have an analysis that is automatic, trustworthy, so using formal methods, and also practical, so that runs on wide variety of examples. The typical workflow for a resource-bound tool is that you have your resource analysis, you feed it the source code of your program, then in the end you get a resource bound. Now, if you want to use formal method to have strong guarantees, you can either verify your resource analysis, but we found this to be quite hard because resource analysis usually involve plenty of heuristics since the problem is undecidable, and they are also relying on complex invariance. So what we propose to do instead is to, together with the resource bound, generate a certificate. This certificate is kind of a justification that the resource bound is valid for the program. And then we feed this certificate, the resource bound, and the program source into a trusted checker. So in our implementation, we use the Coq Proof Assistant. The Coq Proof Assistant grinds and hopefully validates the resource bound. So this validation is expressed in a Coq file as a theorem that states that the resource bound is valid with respect to the semantics of the source program. So we implemented this in a tool called Pasties. You can ask me for the acronym. It takes LLVM bitcode in input, and it infers polynomial bounds and generates certificates. So we evaluated on a state-of-the-art benchmark against like other state-of-the-art tools. And while it's not the best, we think it's doing okay. And more than being okay, it actually generates proof certificates, something that the other tools are not yet able to do. So let me sketch a brief overview of the technique that we're using in the work. It's what we call automatic amortized resource analysis. So plenty of tools are based on this technique, and it's derived from the potential method introduced by Bob Targent to prove amortized complexity. The advantage of the technique are that you can reduce the bound inference to efficient LP solving, that it naturally handles amortized complexity because it's based on this potential method. It also handles non-monotonic resources like memory, where you can free them during your program execution, so you end up having a bound on the peak usage. And it also handles mutually recursive procedures and functions very naturally. The contribution of this specific work are what we call rewrite functions. So it's a technical device that we use to encode program invariants inside the automation. And we also generate Coq certificates for the first time. And we have polynomial bounds, so the previous iteration of this work could only derive linear bounds. We can also infer lower bounds. So now let me be a little more formal about the setting. So in the presentation, we are going to view the resource bound problem as a size change analysis. So if you since you can represent your resource with a number, we actually instrument the program to keep a resource counter and increment it every time we use the resource. So in this example program, that would be the running example. The resource counter is Z, and we are counting the number of loop iterations. So then your resource analysis problem becomes bound the final value of this counter variable Z. In this example, the bound is max of 0 and x, because if x is initially negative, you never enter the loop. But we will assume in the rest of the talk that x starts non-negative for the sake of presentation. We will also see programs as control flow graphs. So this is the source program, the running example. I put blue dots at the various program points, and each of these points becomes a node in the control flow graph, and the actions that the program can take are labels of the edges. So we also have this if action that is a guard statement, doesn't change the memory state, but blocks the execution if the condition is not met. So this is how we represent programs. Now let me give you an intuitive idea of how the potential method works. So this is an execution. So each of the red circles is an execution state or configuration, and it's a pair of a program point, so A, B, C, A, D, and a memory state, the sigmas. So you can see, because you have loops, you can go multiple times through the same program points. In this example, for instance, we go 2 times through A. To each program point, the potential technique method associates a potential function. So this phi, so it's bound to each program point in your program, and this potential function maps memory states to numbers. And the idea is that in the end, when you go through an execution like this, and you apply the potential the potential function of your current point to your current memory state, then you get a decreasing sequence of numbers. And to reach our goal, we set the final potential, the potential of the final configuration of your program to be this, the value of the resource counter. And you can see that by transitivity of these inequalities, your initial potential here, the potential of your starting point, is going to give you a bound in terms of the initial state, sigma 1, on your resource counter Z at the end of the program. We call the final potential the goal potential because here I only use Z, but for instance, if you use minus Z, you get a lower bound on your resource counter. So how do we enforce these conditions, these inequalities? We use what we call these admissibility conditions. So the admissibility condition is defined from an edge. So if you have an edge, A, B, that change the programs, the memory state according to this function f, we want to have that the potential of A is greater or equal to the potential of B after we perform the action of the edge, so that we enforce the inequalities of the previous slide. And for all memory states. So we can rephrase this functionally as this simple condition. And it's actually similar to what you would have when you do when you're using program logic. These conditions are quite simple, and they are local. They are defined only for one edge. So so when we have the full annotation of a program, the full potential functions for all the points in the program, we only have to check this very local condition and simple to validate that we indeed have a resource bound. And so they form ideal certificates. So now let's annotate the running example. So we start from the final state, and as I said, the potential of the final state needs to be this resource counter, because this is what we are bounding. Now, if I have another program point before that transitions to this final point without performing any action, any change on the state, I could reuse the same annotation, but I can also use another annotation that is larger, another potential function that is larger. So here, yeah, I represent potential functions as expressions of program variables, but the intended meaning is that it's a function. And so this is larger than this, assuming that x is greater than 0, and this would be a program invariant that we need to prove through regular techniques like abstract interpretation. So we call this operation of increasing the potential a weakening operation. Now, if we have an edge with a program action like this one, where we increment the resource counter, we have to change the potential function to account for the stage change. So the updated potential function, z plus x plus 1, you might think that the plus 1 is on the wrong side, but state transformation transform predicates backwards, but the transform memory state forwards. It's a bit confusing, but if you want to convince yourself, you can set z and x initially to 0. This evaluates to 1, which is indeed an upper bound on the value of on the final value of the goal. The z ends up being 1. Now another state changer action, so similar reasoning, and we associate the z plus x. Now we have this guard action that doesn't change the memory state. We can reuse the same potential function. And this is, in fact, the loop head of our running example. In fact, the loop head and the weakening point have the same annotation. So this complete potential annotation is valid for the program where I add this back edge. What we found is a loop invariant. And now if I want to complete the running example, I have to account for the initial assignment, z equals 0, and we get the bound x over the final value of the counter. How do we automate this reasoning? Because this last weakening step is kind of coming out of nowhere. So how do we automate this inference? The idea is that we reduce the problem to LP solving. To do this, we need to encode each of these admissibility conditions as linear programs. So the first step is to take a template form for your potential functions. So here we take like linear combination of more elementary base potential functions. And these base potential functions are generated by a heuristic in our tool. These k coefficients are fresh LP variables that are inferred by the solver. The second step and the third step are to encode these operations, the functional composition and the inequality as linear programs. For the functional composition, we decompose the action of composing f on each of the base functions. Then we combine everything together using standard linear algebra. For the inequality, we use program invariance, and we use this new contribution of ours, the rewrite function, to encode this program invariance as linear programs. So I will now glance over some of the contributions, in particular the rewrite functions and how our Coq certificates work. So the rewrite functions, I think I'm just going to say what they actually provide, but not how they work. If you want to know how they work, you would have to take a quick look at the paper. So they are a convenient way to encode program invariance as a set of linear constraints. And this is essential for the automation, in fact. They are also the essence of weakening in previous systems that are based on the previous automated system that are based on the potential method, and maybe more formally, any weakening rule that you had in a previous system, you can always express it using this mechanism of rewrite functions. And through a hinting system, they allow the user to interact with the system. In particular, when the inference fails, you have the possibility to add hints in your program source that do not compromise the safety of the overall analysis, but possibly enable the tool to get a bound. And you have more details about this and how they actually are implemented in the paper. Now the Coq Certificate, so starting from the full annotated program written by the LP solver, what we do is that we take all these potential functions and we bundle them into a certificate. So it's just essentially pretty printing to a Coq file. And then we feed this certificate to the Coq proof assistant together with a support library that, for instance, contains the operational semantics of the programming language. And together with the program source, we run the Coq proof assistant and eventually prove a theorem that says, okay, X is a valid resource bound for your program. So the contributions, we have the first resource analysis tools that produces certificates in a foundational proof assistant, so like proof assistant like Coq with a proof object. And we have a competitive and practical implementation that takes LLVM bitcode and produces polynomial bounds. And we also have a user interaction through these rewrite functions. In the paper, you can find more details about the automatic inference. In particular, we fully expand the complete linear system, linear program. And you can also find how we handle mutually recursive procedure calls that I did not explain in this talk, and how the user interaction works, and more statistics about the experimental evaluation. Yeah, that's about it.
So we have time for questions. I guess I maybe have a few. So it works on LLVM bitcode. So does it mean I can take a simple C program and compile it to LLVM?
That's exactly what we do. Yeah.
Push it through a tool and it will work?
Yeah.
Oh, nice. And okay. So what were your benchmarks for experimental evaluation? Is there a standard set or?
So the benchmark is something we took from a previous paper from Florian Zuleger. It was a benchmark for the Lupus tool, and it's essentially I think the MyBench benchmark for embedded systems. So it's a standard benchmark for compiler benchmark that was processed in such a way that it's applicable with many resource analysis tools.
Okay, and did your proof certificates find any bugs in your tool, or was it all good?
I did find one bug, but it was not. It was in my homemade abstract interpretation procedure that was buggy, of course, because I don't know what I'm doing.
Oh. We do have a question there.
Right, so you claim that this is the first tool that produces these proof certificates. So I'm guessing like a tool like Lupus, under the hood, it's computing an inductive invariant, and you can just spit it out and then check it with an SMT solver. So could you comment on what other tools are producing as a proof? I think,
so other tools are not producing anything. There is this key tool, I think, that is producing certificates. It's not exactly certificates, it's proofs in another verification tool. But for instance, for Lupus, they don't generate anything except the resource bound. I mean, maybe you can get a trace of what they are doing, but there is no formalism for the operational semantics of the program, for instance, and there's definitely no final theorem in any verification tool, whatever.
Okay. By the way, that's a really nice acronym, and thank you.